Hello students, welcome to the heat transfer lab. We are going to discuss the experiment number 6, that is the test on Stefan-Boltzmann apparatus. Aim: to conduct a test on the given Stefan-Boltzmann apparatus and find out Stefan-Boltzmann constant. Okay, so this experiment is related to the thermal radiation. So here we are going to find out the Stefan-Boltzmann constant. Okay, you know that the thermal radiation, that Q is equal to sigma into A into T1 to the power of 4 minus T2 to the power of 4. This is the equation. In this equation, that sigma value is there, that is the Stefan-Boltzmann constant. That value you are going to find out. Okay. So here some specifications are given. The hemisphere diameter 20 centimeter and base plate diameter is 30 centimeter. Test disc diameter is 2.2 centimeter. Thickness of test disc is 1.35 mm. Thermocouples of hemisphere is T1 to T4 at 4 numbers. And thermocouples on disc, that is T5, it is 1 number. And thermocouple in water heater tank, that is T6, that is 1 thermocouple. Okay, so what is the principle of this? According to Stefan-Boltzmann law, the thermal radiation, that is heat flux of a black surface, is directly proportional to the fourth power of its absolute temperatures of the surface. That is given by, I already told, that is QA is directly proportional to T to the power of 4. So if you take Q by A is nothing but heat flux, that is what it is considered, small q is equal to sigma into T to the power of 4. If you remove the proportionality, it will get one constant term, that is sigma, and it is watt per meter square, where capital Q is heat transfer rate in watts and A is the black body surface area in meter square, and where T is the black surface temperature in Kelvin and sigma is Stefan-Boltzmann constant, and the value is fixed, that is 5.67 into 10 to the power of minus 8 watt per meter square Kelvin to the power of 4. Okay, so this value, above sigma value, we are going to find out. We have to prove it. So when the test disk is at steady state, the radiant energy is absorbed by the disk is equals to the radiant energy emitted by it. So this is nothing but energy balance. Okay, so we can calculate surface temperature. What are the surface temperature in this hemispherical surface? That is T1, T2, T3 and T4. You take the average by 4, that is 4 divided by 4, you will get average surface temperature. So then you have to find out heat transfer rate between the disk and enclosure at a steady rate. That is Q is equal to sigma A into T S to the power of 4 minus T D to the power of 4, where TD is nothing but the disk temperature. Okay, it is in Kelvin. Which disk we have to consider? That is T5. And area is pi d square by 4. Okay, the disk area, that it is in meter square. If the disk has mass m kg and specific is C joules per kg Kelvin, then the rate at which heat is absorbed by the disk is Nc delta T by dt. Okay, the value of dt by dt is obtained by plotting the temperature phi versus time curve and taking its slope at t is equal to 0. What we have to do to calculate the dt by small dt, that is temperature gradient, which is obtained by plotting the graph by temperature T5 versus time curve. Okay, so we have to take the slope at t is equal to 0. Then what will get it? Mc dt by dt is equal to sigma A T to the power of 4 minus Td to the power of 4, and equate it to sigma, that is Mc dt by dt divided by A into T S to the power of 4 minus Td to the power of 4. So this is the numerical analysis, how you are going to get the value of sigma. So now let us discuss how to conduct this experiment. Here first step is blacken the disk surface if needed. If it is not black, you should make it black by coating some paints or material. It should be black. Okay, then only it will be get proper results. Okay. Second one is fill the tank with water after closing the valve V1 and switch on the mains and check whether all 6 thermocouples are reading correctly or not, as usual the previous experiment how you have followed. And fourth one is switch on the water heater, and we have to wait some time to get heated up water. Okay, after water has been heated to 90 to 95 degrees centigrade, switch off the heater, and after making the valve making sure valve V2 is closed, then open the valve V1 and fill the jacket with the hot water. Next step, seventh one is take readings of thermocouples on hemisphere, that is T1, T2, T3, T4 for every 5 minutes until get steady state. And eighth step is on steady state, insert test disk and switch on beeper. Okay, so take the temperature of this test disk and T5 for every 5 seconds till steady state. Once the steady state, again take T1, T2, T3, T4. So switch off the mains, open the valve V2 and drain the water. And finally use final steady state values of T1, T2, T3, T4 and T5 for the calculations. So here some observation table, that is mass of the test disk M is equal to 4.464 grams and specificity of the disk material is given at temperature T5, that is 385 joules per kg Kelvin, okay, or degree centigrade. So this is the specific heat is given. We have to observe these two things, and we have to tabulate two tabular columns for different temperature T1, T2, T3, T4 at a different time interval of in minutes, and another time tabular column is there at point T5 temperature for every instant time 5 second, 10 second, 15 second, 20 second, 25 second, like that, so on. You have to take the reading. So here how to plot dt by dt to get that slope at t is equal to 0. So by plotting this graph you will get the ratio of dt by dt, that is temperature gradient, that is required for the equation. So that value you have to supposed to substitute and get the value. Okay, and result of this experiment, Stefan-Boltzmann concept, you have to keep it. Thanks for watching this video. So welcome to the heat transfer lab. Today we are going to discuss about the experiment on Stefan-Boltzmann apparatus. Already you know that who is that Stefan-Boltzmann? He is a scientist. He found the radiation constant, that is sigma is equal to 5.83 into 10 to the power of -8 watt per meter square Kelvin raised to 4. This is the value he found, and here this is only applicable for the black body. The Stefan-Boltzmann constant is applicable for black body. Here the apparatus is like this. Here the top of this equipment, the coil is there. In coil we have to pour the water here. So you can see here coil is there. So you have to fill the water. Once if it is fill the water, here below the apparatus, that black disc will be there. In that, hemispherical structure of the disc will be provided. So from that, once the hot water is entered into the disc, so how much radiate is transferred from the surfaces, that we are going to find out. Okay, let us start this equipment. So first, initially we have to wait for water get heated up. So water is get heated up to 90 to 95 degrees centigrade. That can be measured by using thermometer. So once it is shown 90 to 95 degrees centigrade, then we have to stop heating the coil. Okay. After that heater, we have this is the valve 1 and this is the valve 2 at the drain. So we have to open this valve. Okay, so the hot water is going to enter into this disc. So through that hot water, the radiation is taking place by the surface. So here the temperature readings are there, T1, T2, T3, T4, T5. So these readings are we are going to take down as is once you get the steady state condition, you have to take the set of readings for different time intervals. And beeper is why it is sounding because so every beep we have to take the unknown test readings. Okay. So after that we have to close this valve and this will be open so to drain the water outside. So based on this values test readings we have to do the calculation. Here the tabular column is there and observation also is there. So observation is that what the mass of the test disc we have to maintain. So if you know the mass of the disc, we have to find out the specific heat of the material also we can calculate. Okay, what is the specific heat of the disc? Already it is given at that temperature, that is 385 joules per kg Kelvin degree centigrade. So here the tabular column T1, T2, T3 and T4. So various temperature points at different time intervals. So here the temperature of the T5. So T5 is the which is we are taken from the below the equipment, that is disc. Okay, the temperature, and we have to plot the graph to find out the temperature gradient. That is helpful for to calculate the sigma. So you know that sigma is the Stefan-Boltzmann constant. This is the formula. We have to substitute all the necessary data in this equation to get the Stefan-Boltzmann value. Okay, so once you get the values from the readings, we have to note it down, and every time intervals 5 minutes or 10 minutes you have to take the reading until it gets the steady state condition. For this steady state condition readings only you have to consider for the calculation. So what is that equation for? So here the temperature we can calculate by this mean temperature, surface temperature, that is T1 plus T2 plus T3 plus T4 divided by 4, and where MC delta T by dt is the thing, but specific heat MC and mass, specific heat and temperature gradient is equivalent to radiation of the surface, that is energy balance. This equation gives the energy balance. This is also Q and this is also Q. So from the TS and time graph we get this plot. Okay, we can observe this nature of the graph. So from this we can find out that temperature gradient, and that will be substitute in this main equation, and M and C both are given in the problem observation, and A is the area of the disc surface, and these are the temperature difference of radiation. Okay, so after once you substitute all the values you will get the sigma value. This is the Stefan-Boltzmann's value we get from this experiment. Thanks for watching. Hello students, welcome to the heat transfer lab. Today we are going to discuss calculation part of Stefan-Boltzmann apparatus. Here the observation is given, that is mass of the disc in M, that is 4.46 grams, and specific heat of the disc material at T5 degree centigrade is 385 joules per kg Kelvin. And here the tabular column for the T1, T2, T3 and T4 temperatures. At every time lapse of 5 minutes, 10 minutes and 15 minutes we have taken the reading, that is 71.4, 83.1, 83.4 and 75.5 for the first reading, and second reading, that is 68.4, 68.6, 69.4 and 69.5. Okay, and the third reading, that is 15 minutes, 64.2, 64.2 and 64.2 and 65.7. So here the steady state will be getting from this reading, so that we have to consider for the calculation. And one more column is there, that is for temperature at T5 degree centigrade. So here for every 5 seconds, 10 seconds and 15 seconds, 20, 25, 30, 35, 40 seconds. So we have to take the readings, what will be the temperature. So here you can see 33.7, 33.8, 33.9, 33.9, 33.9, 33.9, 33.9, 33.9. So here almost it is steady state condition for the T5 degree centigrade. So let us do the calculation for this. So calculation is, to calculate T5 you must take the average of this, that is T1 plus T2 plus T3 plus T4 divided by 4. So it becomes 64.98 degrees centigrade. That is, if you want to calculate it in absolute temperature, you add 273, so you will get T5 is equal to 337.95 Kelvin. Okay, once if you calculate the T5 temperature, you can calculate the Stefan-Boltzmann value, that is sigma is equal to mc dt by dt divided by a into ts to the power of 4 minus dt to the power of 4. Here the mass, that is of the disk, is 4.464 grams. We have to convert it into kg, that's why we have taken 10 to the power of minus 3, and specific heat, that is 385, and dt by dt is 0.02. Okay, so this value you are getting from the time graph, TAS minus versus T. Okay, so divided by 3.801 into 10 to the power of minus 4 and 337.98 to the power of 4 minus 307.4 to the power of 4. So sigma is equals to 2.199 into 10 to the power of minus 8 watt per meter square Kelvin raised to 4. So this is how you are going to calculate the value for the Stefan-Boltzmann. Finally, you have to calculate the graph from dt by dt is at t is equal to 0 become 0.02, that we have to consider in the main equation. So this is the desired answer for getting the sigma value, that is 2.199 into 10 to the power of minus 8 watt per meter square Kelvin raised to 4. Thanks for watching this video.